All right then. Now we are coming again to an example of Amperes Law. I believe it's the last one, I'm not sure. We have here a very large sheet, very wide, very long, and it has uniform charge density plus everywhere charge density sigma. And it is moving in this direction with a speed v. If I look from this direction, I would see here that width w coming towards me. I would see the velocity vector coming towards me. So this thing is coming towards me, and it is uniformly charged with charge density sigma. Now I have to choose cleverly a closed loop in order to apply Amperes law. This dotted line is in the surface. I go up by a certain distance d. This here has a certain length L, which I can choose arbitrarily. This is d. I go down over a distance d. I come below the surface, again distance d. I return and I go up here. This is d, this is L. It's really easier to draw it here. So this is d, d, L, L. Well, it shouldn't be hard for you to convince yourself, which is by convention, that the B field here must be in this direction and that the B field there is in this direction. Now what I'm going to do, I'm going to do the closed loop integral of this loop, and I'm going to choose a flat surface to calculate the current going through that flat surface. So that's this flat surface. As the belt moves, charge is going through. You can calculate how much charge goes through per second. But I also am going to make d very small. I'm going to make d going to 0. So that means when I make this integral b dot dl, I have simply b times l because they are in the same direction, so the dot product simply gives me a cosine of the angle 1. 0 here because I make d 0, very small, and then I have another bl here, because they again are in the same direction, and that now equals mu 0 times the current through that surface, I through. Well, I through is the charge that going through that surface per second, and that equals L times sigma times V. And you should be able to convince yourself of this very easily, and so that leads then to a magnetic field, which is mu 0 times sigma times V divided by 2. Notice, the faster the belt moves, the higher the current is through this surface, the higher the magnetic field. The higher the surface charge density, the higher the magnetic field. Notice also it's the same on both sides. There is no dependence on z. If I call this z, there is no dependence on that. This is slightly similar to the case that we had earlier, whereby we had a very large plane uniformly charged with a positive or negative charge. We also there had that the electric field, provided that the sheet is large enough, is independent of z. It's the same above the plane, pointing upwards if it is positive charge, and down the plane it is pointing downwards, but the magnitudes are the same. And you see something very similar here. This is that factor 2. For an infinite charged plane, the electric field, you may recall, equals sigma divided by 2 epsilon 0. Now, if you accept the fact that the magnetic field is independent of Z, you could also argue that if there is a magnetic field here and if the sheet is very long, that even if D is not very small, that B would always be perpendicular to D here and here, and therefore the dot product would disappear anyhow. So even though I made D going to 0 to convince you that there would be no contribution here of integral B dot dl, if you had accepted the fact that the magnetic field here is always in this direction and here is always in this direction, not necessarily accepting the fact that they have the same magnitude on independent of Z, you would still agree that B and dl here would be perpendicular to each other. And therefore there would be no contribution. But now you have to finish this problem. You have two sheets. Oh, there goes my button, that's not so good. I have here two sheets. This has again sigma, and I have another one, also huge in size, also plus sigma, uniformly charged, but one is going in this direction, and the other one is going in this direction. We have a point A here, we have a point D between the plates, and we have a point C below the plates. I avoid the B here because I don't like B's when we deal with magnetic fields. Well, assume that these sheets are infinitely large, so you can calculate what the magnetic field above this one is and below this one, and you can do the same here, and you obviously apply the superposition principle. And if you apply the superposition principle, it's immediately obvious that at A, the magnetic field must vanish, because the two plates create a magnetic field which is the same but in opposite direction. It will also vanish at point C, but of course between the plates the two fields will enforce each other. I don't think you're going to have too much trouble with this one. I think it's about time that we start talking Faraday's law. No, not yet. We're close, but not yet. Professor Becker invented a cute problem of a cylinder which has a certain length L. It's a hollow cylinder and it is rotating with angular velocity omega. Its radius A, and there is a surface charge density plus sigma only on the surface of the shell of the cylinder. You're being asked what is a magnetic field inside and outside the cylinder. Now first I would like you to read up on page 920, because this is very similar to a solenoid. A solenoid are windings, separate windings, and currents are going around in a spiral. Well, here this drum is going around, so this is also currents going around. I'm going to solve this for an oversimplified case whereby L in my mind is going to infinity, very, very long, and I'm going to apply Amperes Law, and I have to choose a very, very clever loop. Here is another view of that cylinder, and here is its radius A. It's going around with angular velocity omega, and the loop that I'm going to choose is this loop. The loop I choose is at a distance little r from the center line, and this distance d I'm going to make very, very large. Let this be b, this length, and let this be b. I now have to apply Amperes Law, closed loop integral of b dot dl equals mu 0 times I through. It's clear that this is going to be my surface, and I have to calculate the current going through that surface, but that's only right here where charge is moving through this surface inside the plane. Well, the magnetic field, by convention, must be here in this direction. The magnetic field here, if I'm very, very far away from the cylinder, clearly has to be 0. And the magnetic field here, well, if there is any, it would have to be in this direction for reasons of symmetry. Well, here it is clearly everywhere perpendicular to the dl if I go around in this direction, and it's everywhere perpendicular to the dl if I go in this direction. So there's no contribution to this term of this part, of this part, and of this part, because b is 0, so I only have a contribution here. So what do I get is that b at that location r times b equals mu 0 times I through, and I through equals sigma times v times b. And if you want to write down for this omega r, that is fine. Omega, not r, but a, sorry, it's not r, but it is a, because the current goes through here. So the velocity there is omega a times b, br times b, and clearly you see you lose your little b, of course, because Faraday's law doesn't care about how long you choose this loop. So here you see that the magnetic field increases when omega goes up. That is intuitive, and it also increases if you had more surface charge on your cylinder. Now, what happens now with the magnetic field just outside the cylinder? In other words, if I don't make d very, very long. Well, what may not be so intuitive, that if indeed the cylinder is infinitely long, but only then the magnetic field outside the cylinder is to a good approximation 0. Here is now this surface, this closed loop. I again have a certain distance r here, but I have already shown that b of r, for r smaller than a, is independent of r. Notice, when you look at my previous result, that there is no little r in here. So it's constant inside this cylinder, just like it was constant inside the solenoid, to a reasonable approximation. This is b, and this is b. I'm going around like this. This is my surface. And so I'm going to get that b. I call this magnetic field here inside times b. This part is 0 because the dot product is 0. Here I have a b outside. But since b outside and my dl are in the same direction, I get b outside times little b. That now equals mu 0 times I through, which we just calculated. But we already showed that this is the same as that in the previous calculation. So there's only one possibility that this is 0, and so the magnetic field outside the solenoid, independent of how far you are away, equals 0. And I really strongly advise you to again read up on page 920, where we have cases where the cylinder is not infinitely long, the solenoid is not infinitely long, and then you do see magnetic fields here leaking out, so to speak. Very well. There is a way, perhaps, that I can make you see in an intuitive way why the magnetic field outside may be 0 if the sheet is infinitely long. This is just my attempt to give you perhaps some insight so that you don't feel that you're sort of being cheated, perhaps. Would you agree that right here at the edge, the cylinder goes into the paper, so there is a current going into the paper? Would you agree that right here at this edge, where the cylinder is coming towards you, there is a current coming out of the paper? By convention, if there is a current going into the paper, the magnetic field is down here, the magnetic field is up here, and the magnetic field is up here. Now imagine that this was an infinite sheet, which it's not. Then B and B and B would have the same magnitude, except that the directions are different. I can do the same for this current. The B would now be pointing upwards. the B here would also be pointing upwards, but on the left side the B would be pointing downwards. And you see that you get outside 0 and that inside the two magnetic fields, due to this current going into the paper and this current coming out of the paper, support each other. Very similar to what we had earlier when we had very large capacitor plates, very large in size, linear size L here, much larger than the distance d. We had positive charge here, negative charge here. Remember, for the same reason, E was 0 here, E was 0 there, and the electric field inside of the two plates support each other and was sigma divided by epsilon 0. Superposition principle again in case of very, very large plates.